The circumstances created by poor weather conditions on the ground, blowing and drifting snow, and icing conditions in flight require forethought and knowledge, additional preparation. Cold soak is defined as a continuous extended exposure to low temperatures during which the aircraft is parked without system operating. Cold soak and subsequent airplane power-up, engine start and after-start procedures have been demonstrated for the Phenom at -40 degrees Celsius, -40 degrees Fahrenheit, following 10 hours of exposure. Tests in natural ice conditions and with simulated ice shapes have demonstrated that the Phenom exhibits satisfactory handling characteristics during operation in ice conditions. This video features pertinent aspects regarding cold soak operation. As well, it covers the most important aspects regarding flight in icing conditions, expanding or reinforcing previously published information to assist flight crews in pre-planning and operating the Phenom aircraft in adverse weather. In this video, we will take a look at icing from several points of view. Our goal is to ensure that you understand the basics of the icing environment, the principles of flight in icing conditions, and the effect of icing conditions on aircraft performance and handling, to allow you to safely operate the Embraer jet. A review of the icing phenomena. Icing conditions are defined by the airplane flight manual based on static air temperature for ground operations and total air temperature for in-flight operations. Icing conditions may exist if SAT and TAT is 10 degrees Celsius or below, along with prevailing conditions on ground or in flight. The general rule is that icing accumulation is always greatest at temperatures not too far below 0 degrees Celsius, 32 degrees Fahrenheit, and usually is negligible at temperatures below about -20 degrees Celsius, -4 degrees Fahrenheit. Contamination on ground can be caused by falling wet or dry snow, slush, frost, freezing rain or drizzle, and the cold soak effect. Frost is a crystalline, light layer of ice which can form on almost the entire aircraft when the temperature of the exposed surface is below freezing, while the free air temperature may be above freezing. Significant deposits of ice can form on the wing upper or lower surface after the fuel is cold soaked in flight, during a ground turnaround, and can occur when the outside air temperature is above or below freezing. Ice that can form below a layer of snow or slush may be difficult to detect. Ice which builds up on fan blades and inlet lips can damage the engine when it is started. Any ice contamination on the aircraft prior to takeoff may have a detrimental effect on aircraft performance and handling. Airframe icing occurs when supercooled liquid water in the air adheres to or accretes on the surface of an aircraft. In flight, ice accumulation on an aircraft depends on many factors. The amount and shape of accumulated ice is a function of the concentration of supercooled liquid water in the cloud, droplet size, distance flown in icing clouds, collection efficiency, airspeed, and temperature. Basic principles of ice accretion can be described this way. Small droplets normally accrete on the airfoil near the stagnation point. Often, the tiny cloud droplets escape over the airfoil section without accreting on the aircraft. Larger droplets, with their increased inertia and impact over a larger percentage of the chord of the wing, often accrete well beyond the stagnation point. Therefore, larger supercooled droplets can produce more serious icing encounters as they produce more ice to be collected on the wings. Icing from a cumuliform cloud frequently has a high liquid water content on large droplets. Thus, flight in a cumuliform cloud leads to an increased potential for moderate and severe icing throughout most of the depth of the cloud. This is especially true during the developing stages of cumuliform clouds. The greater the distance flown in an icing cloud, the greater the amount of ice collected. This is typical when flying in a stratiform cloud with its layered development. Icing accumulation in a stratiform cloud is most often light to moderate. Stratus might have an exception when forming over lakes, as they may have very high liquid water content available from the moisture rising from the lake. Stratus clouds with a vertical development greater than 3,000 feet are rare, so an altitude change of just a few thousand feet may take the airplane out of icing. It is extremely important to note that the most severe icing intensity in stratus clouds normally occurs near the tops of the cloud layers. The accretion rate also depends on the location and geometry of the surface of the airframe. A relatively large airfoil has low ice accretion efficiency. A narrow radius leading edge has a greater collection efficiency. As a result, tailplane with a sharper leading edge section will usually accrete ice before it is visible on the wing, and at a higher rate, which usually results in a greater ice thickness on the tail than on the wings. The supercooled liquid water content also affects the rate of ice accretion. The high water content of the cumuliform clouds with large vertical development can cause ice to accumulate much more rapidly than in a stratiform cloud formation. Therefore, icing in cumuliform clouds can be light, moderate, or severe. Orographic clouds, which form by moist air flowing up the side of a mountain, and wave clouds, recognized by their wavy tops, can have high liquid water content. Continued flight along these clouds may result in airframe icing. Cirrus clouds are composed of ice particles and should not result in ice collection. But the possibility of run-back icing from refreezing of particles, which melt on heated surface, is a possibility when flying through these clouds. Local temperatures, droplet size, and supercooled water content are the factors which most influence the type of ice accumulated on the aircraft. Low temperatures, total air temperature between -10 and -20 degrees Celsius, low liquid water content, and small droplets tend to result in rime ice, which has a rather milky, white, and opaque appearance. Warmer temperatures, total air temperatures between well above freezing and down to -10 degrees Celsius, high liquid water content, and larger droplets tend to result in glaze ice, which often has a clear, shiny appearance. Rime ice is more often found in relatively cold stratiform clouds, while glaze icing is most often found in cumuliform clouds. However, as previously mentioned, it is possible to encounter moderate to severe icing near the tops of stratiform clouds. Flying in a stratocumuliform cloud results in a mixture of rime and glaze ice, which is appropriately called mixed ice. Mixed ice can also occur in many other meteorological situations, where the ambient conditions vary over short distances. Cloud droplet sizes are normally expressed in microns, which is a millionth of a meter. Cloud droplets are typically between 2 and 50 microns in diameter. However, freezing drizzle and freezing rain droplets as large as 1,000 microns, 1 millimeter, can occur. Freezing rain and freezing drizzle are large supercooled water droplets, commonly referred to as SLD, which impact with aircraft surface to cause rapid and extensive ice accretion. Icing associated with freezing drizzle and rain is severe icing because aircraft are not designed or certified to handle icing from supercooled droplets that large. Freezing rain is normally associated with temperature inversion. The rain falls from the warm air above into sub-freezing air below. Freezing drizzle forms when liquid drizzle drops fall into sub-freezing air. It can also form and exist totally within a cloud that is entirely at or below freezing temperatures. Freezing rain and freezing drizzle differ primarily by droplet size. While the size definition is not entirely uniform, it is important to know that supercooled droplets larger than about 50 microns represent SLD icing conditions. No aircraft is currently tested or certified for SLD icing under FAR Part 25 Appendix C, and consequently these conditions represent severe icing. Evidence has shown that severe icing can be found from 20,000 feet down to ground level, with total air temperature down to 30 degrees Celsius, not only during temperature inversion, but also when a moderate wind shear exists near the top of the clouds, as well as in weak cumulus clouds embedded within a stratiform cloud layer. Any encounter in the form of freezing rain or freezing drizzle constitutes severe icing and requires immediate action by the flight crew to exit these icing conditions. Continued flight in freezing rain and drizzle, or any supercooled droplets larger than 50 microns, is potentially very hazardous and must be avoided or exited as soon as possible. Unusually extensive rapid ice accreted on the airframe in areas not normally observed to collect ice, or accumulation of ice on the upper surface of the wing after the protected area should be assumed to come from supercooled large droplets. Handling effect. The consequences of ice accretion on the wing and tail surfaces are immediate if the aircraft anti-icing system is not used. Lift is reduced, drag is increased, stall speeds can increase, and the aircraft pitching moment may change. Let's take a few moments to carefully consider the effect on aircraft handling. In flight, ice will normally accrete in areas around the aerodynamic stagnation point. If ice droplets are big enough, they will strike the wing farther aft, creating a variety of shapes, thicknesses, and textures of ice, effectively changing its shape. Changing the shape of the airfoil will change the airfoil geometry to produce a new airfoil in which the lift, drag, and pitching moment characteristics are different from the wing's designed airfoil. Check the lift curves shown for an airfoil with ice and without ice. Compare the curves and observe the reduction in lift at a given angle of attack and the reduction in maximum lift angle of attack. For example, for a wing covered with insignificant rime ice, only 0.5 mm thick, the maximum lift capacity decreases 33%, and the critical angle of attack is reduced in this case from 13 to 7%. This shows the degree of potential hazard from a relatively small amount of ice on the aircraft wing. Ice causes a similar effect on drag. Drag varies greatly from almost no increase to a more typical 100% increase, resulting from rime ice, and 200 to 300% for clear or glaze ice. The overall effect of ice accumulation on the wing is quite obvious. If the aircraft anti-icing system is not used, ice accretion can increase stall speed, resulting in a potential for a premature stall at a lower angle of attack. To cope with this situation, the Phenom jet stall warning system is triggered at a lower angle of attack in icing conditions. This protection is activated when the wing's ice protection system is on and is displayed to the pilots by a dedicated message. The responsibility for ensuring a clean aircraft rests with the flight crew. Operating regulations clearly state that no takeoff is allowed when snow, ice, or frost is adhering to the aircraft. This is known as the clean aircraft concept, and it is essential for safe flight operation. The primary method for the flight crew to ensure a clean aircraft is through close visual and physical inspection of the critical surfaces prior to takeoff. Even at intermediate stops, an external walk-around is necessary because of the possibility of ice forming after landing from either cold soaking frost, conventional frost, or precipitation freezing on the aircraft. Although some of the following tasks might be considered a maintenance function, flight crew is supposed to take additional care and inspect those areas where ice or snow will degrade aircraft performance, and carry out himself or herself the task if no maintenance support is available. When approaching the airplane, evaluate it from a reasonable distance. Watch the area where the airplane is parked and evaluate if there is room for the taxi-out or pushback maneuver. Make a complete walk-around following the established procedures. Remove all protective covers from the engine air inlet and outlet, pitot probes, static probes, and pitot-static probes. Check if pitot tubes, angle of attack vanes, and static ports are clear of ice. Check residues of icing and anti-icing fluids in these areas. Ice buildup or gel close to pitot and static ports may disturb airflow over the sensor, resulting in erroneous readings even when the sensors themselves are clear. Visually check that fuselage, wing upper and lower surfaces, tail and control surfaces are free of ice, snow, or frost. Polished frost is not allowed. In addition, as no contamination is allowed on the wing, carry out a hands-on inspection. Do not touch the surfaces with bare hands, as the skin may stick to a freezing surface. This first evaluation will tell you if applying de-icing fluid is required. Prevailing and forecast icing conditions will give directions if it is necessary to apply anti-icing. Call for de-icing and anti-icing application in advance to make the local service providers aware of your necessity. Inspect control surfaces, gaps, and hinges for signs of residual fluid or gel. Ask for maintenance assistance to remove residues if any deposit is discovered. Hoar frost, thin enough to allow distinguishing painting and markings underneath, is allowed on the fuselage. Hoar frost is a uniform, thin, white deposit of fine crystalline layer that forms on exposed surfaces during calm, cloudless night. If necessary, remove snow or frost over the wing filler cap to properly open it. Use hot water to defrost or simply scrape the region with care not to damage the wing or the filler cap. Flying at high altitudes can cause suspended and dissolved water to condense out of the fuel and form free water. Water in fuel tanks should be drained frequently and thoroughly. Take the chance and inspect the fuel collected for water globules in the liquid. Check hydraulic accumulator, emergency brake accumulator, and oxygen pressure consistent with outside air temperature. Service fluids as required. Moreover, take a look in the compartment lines for signs of leakage. Check that all engine air inlets and outlets, drains and vents are clear of ice or snow, and that the fan is free to rotate. It will ensure a flawless start with proper N2 indication. Make sure the pylon's vertical fin ram air inlet and the ground cooling fan inlet-outlet are clear of ice or snow. Check landing gear doors, gear locks, and mechanisms are unobstructed and clear of ice and snow. Check tire pressure when tires are at the ambient temperature. It can take up to 3 hours after a flight for tires to return to ambient temperature. A temperature change of 3 degrees Celsius, 5 degrees Fahrenheit, produces approximately 1% pressure change. When tires are going to be subjected to temperatures between takeoff and landing in excess of 50 degrees Fahrenheit, 10 degrees Celsius, it is recommended that inflation pressure should be adjusted to worst case prior to takeoff. Before returning to the cooler climate, adjust inflation pressure for the lower temperature. Install the batteries if they are removed. Refill toilet water tank with appropriate flushing fluid. Adding hot water at a temperature not exceeding 35 degrees Celsius will prevent water freezing during cabin pull-up. Make a normal internal safety inspection, caring about the following. Once the batteries are on, and they are currently the only source of electrical power, the pilot must concentrate on saving the batteries. The use of external power is recommended. PFD and MFD may look somewhat faded, mainly after extended cold soak at very low temperatures. Fading will disappear as displays begin to warm. Engines may be started when engine indication is readable on the MFD or on the reversionary mode of the PFD. Lighting of the displays should be adjusted to full bright to add warming LCDs. Minimum battery voltage to start the engines is 24 volts. A warm battery will render a safe engine start. If the airplane has been cold soaked at temperatures colder than -18 degrees Celsius, batteries must have been kept warm or removed to a warm place. Below -18 degrees Celsius, use external power as an aid in power up and engine starting. In the event oil temperature is below -40 degrees Celsius for starting, it is recommended that the oil be heated to above +40 degrees Celsius, utilizing dry motoring cycle prior to an attempted start. Make a normal engine starting, caring about oil and ITT limits. High oil pressure during cold start is normal, and pressure should decrease as engine warms up. After achieving a stabilized idle under cold conditions, or with cold fuel, below 0 degrees Celsius, remain at ground idle until oil temperature reaches 10 degrees Celsius. During this time, the transient oil pressure limit applies. Run the engine for an additional 3 minutes to ensure that no ice particles are present in the fuel supplied to the engine. Set the air conditioning to warm up cabin interior. Set mode switch to auto. Cockpit and cabin fans should be on high or medium. Set the cockpit and cabin temperature selector to full hot. With the air conditioning properly set, it may take, for example, 15 minutes to heat cabin from -20 degrees Celsius to 21 degrees Celsius. Preheating the cabin will reduce this time. After the electric hydraulic pumps are on, check hydraulic pressure. If the pressure does not rise, warm up the hydraulics reservoir compartment with hot air. Check all flight controls for freedom of movement and full travel. Operate all trim systems. If you feel any restricted movement or jamming, ask for maintenance assistance. Extend and retract the flaps. Make sure they are free from snow or ice before moving them. Turn on and check wing inspection lights. Dispatch is not allowed if you are supposed to fly at night in icing conditions, and any light is inoperative. After the engines have been started and the ice protection test is performed, turn engine and wing ice protection on when icing conditions exist or are anticipated according to the airplane flight manual instructions. Taxiing on ice, snow, or slush-covered runways should be done at the lowest practicable speed, due to reduced braking capability and the possibility of skidding. Taxiing with flaps extended exposes the jack screws to contamination thrown up by the main gear. Therefore, always taxi with flaps up on ice, snow, or slush-contaminated runways. If flaps were left up during taxi, complete the after-start checklist before takeoff. Use minimum thrust to avoid blowing snow or slush on personnel or airplanes nearby. Maintain a greater than normal distance behind other aircraft while taxiing in snow-covered runways. Shortly before the aircraft takes the runway for takeoff, repeat the flight controls check and make a final visual inspection of the wing to ensure that it is clean. When inspecting the wing during your pre-takeoff contamination check, look at the entire wing upper surface and not just the leading edge or wing tip. Although the wing tips can be seen from the cockpit, almost the entire wing is visible from a cabin window. Therefore, it is strongly advisable that a crew member make the visual inspection from the cabin. Additionally, the crew should ask for assistance of trained and qualified personnel outside the aircraft to assist in the pre-takeoff and check to ensure that the tail and fuselage, which are not visible from the cockpit or cabin, are free of any ice contamination. Remember that high winds and jet blast may cause anti-ice fluid to flow off, and other factors can contribute to reduce fluid effectiveness and reduce holdover times. If any ice has accumulated or the holdover time expires, never assume the ice will blow off during takeoff. Return for another fluid application and get de-iced or anti-iced again as the conditions require. Review the takeoff performance analysis to determine the appropriate weight and speeds for anti-ice system on. In a situation where fuel length and surface conditions are not optimal, use maximum allowed thrust. Particular attention and proper assessment is required to cope with contaminated or low-friction runways. Takeoff in a normal manner. Rotation does not require any special technique. As demonstrated by flight tests and icing conditions, the Phenom jet exhibits good handling and responsiveness and requires no special procedures in Appendix C icing conditions when operated in accordance with the airplane flight manual. Once airborne, monitor pitch attitude and airspeed continuously with autopilot on or off. Performance changes such as airspeed decrease, reduced climb rate, and or higher than normal pitch angle may be an indication that ice has already accreted onto the airframe. If ice-related performance decreases are noted, ensure that all systems are selected on and make the required thrust and attitude adjustments. Remember that icing in flight can occur at any time of the year. Therefore, it is necessary for the flight crew to monitor the systems and remain cognizant of ice any time the airplane is in icing conditions, even in the summertime. Visual observation of ice on the windshield pillars, is a clear indication that icing conditions are present and ice is accreted on the aircraft. Verify that the engine, wing, and stabilizer valves are open on the ice protection synoptic page on the MFD. The flight crew should also be alert for visual cues of unusual icing. If ice accumulation is rapid and severe, such that the anti-ice equipment fails to reduce or control the hazard, request immediate clearance from ATC and leave the icing conditions. Remember, unusually extensive ice accreted on the airframe in areas not normally observed to collect ice or accumulation of ice on the upper surface of the wing aft of the protected area should be assumed to come from supercooled large droplets. Again, leave these icing conditions immediately if severe or large droplet SLD icing is observed. Flight crews should be particularly vigilant if icing conditions exist while the aircraft is in a holding pattern. Remember that minimum airspeed in icing conditions is 150 knots indicated. Flaps and gear must be retracted. Should severe icing conditions be encountered during holding, the flight crew must closely monitor the icing and take immediate action to exit the conditions. It is never good practice to continue to hold in icing conditions. The autopilot may mask tactile cues that indicate adverse changes in handling characteristics. Use of the autopilot is prohibited when any of the SLD cues specified before exist, or when unusual lateral trim requirements or autopilot trim warnings are encountered while the airplane is in icing conditions. If the autopilot is engaged, hold the control columns firmly and disengage the autopilot. Review all approved performance data required to land in icing conditions. This requires reviewing associated speeds and special procedures for landing with a failed anti-ice system. Landing on runways contaminated with ice and slush requires that flight crews plan and execute the approach and landing properly to be successful. Fly the stabilized approach concept. It is essential that the aircraft is configured and stabilized passing 1,000 feet AGL. Cross the runway threshold at 50 feet and VRAF and place the aircraft within the 1,000 feet mark. Touch down on the center line to provide maneuvering margin if the aircraft starts to drift because of runway surface contamination, and lower nose wheel immediately. Apply brakes symmetrically. Use proper braking techniques to cope with a short landing distance. If the landing weight is limited by runway length, the use of maximum brake effort is mandatory until it becomes obvious that there is enough remaining runway for the use of milder braking. If no deceleration is felt, hydroplaning might be on its way. Do not use emergency brakes, as it may cut anti-skid protection. Keep the pressure on the pedal brakes until the airplane decelerates. After landing on a contaminated runway or after operating in icing conditions, flap retraction to zero should be delayed until they have been inspected and confirmed clean of deposits of ice or slush. Once you have landed in icing adverse weather conditions, preparing for a cold soak period becomes the next task. Good preparation to preserve the aircraft from the effects of low temperature is the key to avoiding delays. In most cases, it is more economical and time-saving to use a hangar than leaving the airplane outside in the harsh weather. Put wheel chocks in place. Apply parking brakes only in icy ramps. Otherwise, parking brakes should not be applied to avoid freezing of the brakes. Remove from the aircraft any item that can freeze or deteriorate when subject to low temperature. Remove the waste tank if the aircraft will remain soaked below 0 degrees Celsius, 32 degrees Fahrenheit. Proceeds to fuel system draining. Remove the batteries and keep them in a warm place, or have a battery heater connected if the aircraft will remain soaked below minus 18 degrees Celsius, minus 1 degree Fahrenheit. That's it. Be prepared to respond to any icing conditions and review all available material and all information that can assist you in making practical and safe decisions. Continuous flight crew alertness to the meteorological hazards and the effect of contamination on aircraft performance is essential. Close adherence to cold-soaked recommended procedures and knowledge of all aspects regarding this operation is quite important to save time and render a safe flight. Advanced preparation and situational awareness by the flight crew will ensure that safety is maintained during all cold weather operations and especially in icing conditions. Fly safely.